In early days, man worked mainly with the energy in his body. Today, we use many forms of energy which can work for us in a wide variety of ways. We're preparing to shoot a motion picture on energy. Let's see how many ways we are using energy to make the picture. We have our lights and the camera. The energy of human muscles does the work of moving the camera. When the camera is in place, another kind of energy, electrical energy, will do the work of running the camera. Well, there we are, just about ready. We use sound, another form of energy, to talk and give instructions. And now we'll check the lights. Lights use electrical energy. Do they do work? Do they move objects? Not exactly. But strong light does cause the indicator of this light meter to move. So, as we'll see, light, too, is a form of energy. Well, all set? Camera, action. And here's what the camera sees. Some metal balls, some matter, normally at rest. Energy is required to move these objects. Muscular energy lifts the metal ball against gravity. As a ball is lifted, it gains in potential energy, the energy of position. As the ball drops, the potential becomes kinetic energy, the energy of moving objects. This kinetic energy can be transferred through the balls so that the ball at the other end is lifted, gaining in potential energy. Think about what's happening here, and you may have a better understanding of potential energy and kinetic energy. The same principle is used in a pile driver. The kinetic energy that drives the pile comes from the position of the hammer, potential energy. And how is the hammer lifted? By the steam engine, which gets its energy from the chemical energy of coal. Chemical energy can do work when it causes certain substances to react with one another. For example, vinegar and baking soda contain chemical energy. This is stored, or potential energy, when the two chemicals are kept apart. But mix them together, and you see a transformation of a little of the chemical energy into motion or work. A storage battery accumulates chemical energy when it is charged. This is changed to electrical energy when you press the starter button to turn over the motor. And when you step on the gas, the chemical energy of the fuel is changed by combustion into heat energy in the motor, which moves the car. Let's examine this subject of heat as a form of energy. In this laboratory demonstration, we can see heat doing work. This turbine wheel is matter at rest. Heat from the Bunsen burner will warm the water from about 25 degrees centigrade on up to the boiling point. Heat causes the water to turn to steam, which expands and moves the turbine. Expansion due to heat is the basic principle behind all kinds of heat engines. Closely allied to heat are a number of other forms of radiant energy. Radiant energy travels through space in waves of different wavelengths. You've heard of radio waves and television. The energy travels in wavelengths from a quarter of a mile long down to a few feet in length. Infrared rays, a form of heat, are radiant energy with a wavelength shorter than 1/100th of an inch. Still shorter are the waves of visible light, from the longer red rays through the spectrum to violet. Ultraviolet, such as the tanning rays of the sun, is energy with an even shorter wavelength. X-rays and gamma rays can travel through opaque objects and are extremely short, about 1/1000th of an inch. All these waves are forms of radiant energy. We also use energy in the form of electricity. Here, in a simple motor that anyone can build, we see motion caused by the flow of electricity. Electrical energy can be used to do work, to operate such machines as this streetcar. The energy to move a streetcar must be brought from somewhere, through wires from an electric plant, perhaps a coal-fired steam plant, or a hydroelectric plant. Here, electrical energy is obtained from the kinetic energy of falling water. And the whole system, from water to streetcar, might be thought of as a single machine, a machine that transforms the potential energy of water behind a dam into the kinetic energy of a moving streetcar. And the transformation of energy from one form to another is the whole story of our practical uses of energy. We have devised a great variety of appliances, tools, machines, and engines designed to make use of various forms of energy. But what are the sources of our energy? Natural fuels, such as coal, are one important source. Ages ago, energy from the sun, which accumulated in green plants, formed the coal we use today. Falling water may also be called a source of energy. But how did the water get where it could fall? Heat from the sun furnishes the energy which evaporates water from oceans and lakes so that it can fall as rain and flow in our rivers. So the sun is the original source of most energy. Heat and light and other forms of radiant energy result from a process in the sun, a process, we believe, of transforming matter into energy. Indications are that simple atoms of hydrogen in the sun are being built up into helium, giving off enormous quantities of energy in the process. This type of energy is called nuclear energy, or sometimes atomic energy. From the nucleus of the atom comes the explosion of the atomic bomb. But we can demonstrate some very gentle effects of nuclear energy. We use a device like this to measure the radiations of nuclear energy. Indications of such energy are picked up by the tube or probe of this Geiger counter. They are amplified in this box and show up as a warning sound on the loudspeaker. Such a measuring instrument is an important tool in our investigations of industrial and medical applications of nuclear energy. Now, you do not ordinarily think of a watch as radiating energy. Of course, the luminous dial gives off light visible in the dark. Yet the radium paint also sends out other radiations, gamma rays, as the nucleus of an atom here and there breaks up. We shall hear indications of matter, atoms of radium, being transformed into energy. We can also see indications of this radiation of nuclear energy. Rays given off by the radium atoms cause this needle to move. And so we've learned a little about our sources of energy and the forms it may take. We've seen potential energy, the energy of position, transformed into kinetic energy, the energy of movement. We've seen an example of chemical energy. Heat energy. Electrical energy. And nuclear energy. Matter transformed into energy. In this picture, we've shown just a few examples of different forms of energy. Wherever you see work being done, find out how energy is being transformed and how it is being applied. What can you learn about the nature of energy?